So last week we saw how to encode the RISC-V instructions, whether it's addition, subtraction, whatever, right? We saw how it is encoded into a 32-bit instruction format, and then we know all the fields within that 32 bits, right? We know each field stands for something, and then we know that based on the instruction, the format will change. We know that already, right? So we are going to see how it works in the real. We are going to see how it will work when we implement it using a real CPU, right? So I think we know how to make everything here, right? We know how to design every single block here from the scratch using logic gates and using high level hardware description languages, right? And using the tool to simulate it. We can do that already, right? Right? We know how we know how it works from the memory to the register path to the ALU to the data memory. We know how it works, the formatting or the format, and then how the information flows from one end to the other. We know that already, right? Right?
Yes, sir, yes, sir. Said it last.
So when you are designing your hardware in any hardware design, not only in a CPU design, right? You have what is called the control signals, and then you have what is called the data path. You guys know this already. The control data path in any hardware. No, I mean once if you look at this diagram here, right? The data path are the individual components, the memory, register for ALU, and then the data memory, right? How data flow from one side to another or from one component to another is what is called the data path, right? Understood? How data flows from one to another. And then the control is what controls which component to activate based on some particular signals, right? So the memory don't just work, right? The memory is part of the data path, right? But the memory needs some signals for it to work, some enable signals for it to work, the clock for it to work, and some other signals, right? Those are the control. You need to control the memory to work, or the ALU, or the register file. You need to send in it some signals, enable, write enable, read enable, or whatever. Those are the controls. So in every hardware you design, you need data path, the individual components, right? Where data move from one state to another, and then you need the control that will actually control all the individual components when they start, when they stop. Then, right? Do you guys understand? Right, so this is what the computer looks like normally. It has processor with the control and data path. Then we have memory also, right? So here you can see that the memory is made up of the program and the data. Only one memory for storing both your program and then your data, right? So to actually send signals from your control unit, your CPU to the memory, you need some kind of interface, right? Some interface needs to be there in order to be able to send some signals from your control unit to the memory. But that interface is called the processor memory interface, right? And then you also know that we also have to get some signals from outside. Those are the I/O, the input-output signals, the input signals, and then the output signals, right? We have an interface that connects the memory to the input-output signals, right? That is the memory, that is the I/O memory interface. So this is how your typical computer looks like. Understood? And there is just one type of a CPU. There are several types. This is just where the program and then the data reside in the same memory. There are other types you guys already know about, right? Where the program and then the data reside in the same memory. You already know that. Yeah. The von Neumann and that one, that one, you guys know it well, right? The von Neumann and Harvard architecture, right? So this is the CPU, and then its control signals. We have data path, as I said. We have the individual components, and then we have the control unit that activates each individual component of the CPU. right? I think so. In digital system, we have done this already. Information is encoded as binary, ones or what zeros, right? Only ones and zeros. And then we have two types of digital system design. We have what combinational logic, right? Where the output depends on the input directly. Once you give it an input, you get an output directly. We've done this already. And then we have the state or sequential circuits, right? Where information can be stored. The other one does not store information. Combinational logic does not store information. We already know that. But the state or the sequential circuit store some kind of information through the flip flop or latches or whatever. We've done this already, right? And then this is just the basics of. You don't have to go through all this. You guys know this all this already, right? You guys don't know all this already. No? Hey, these are combination logic. The gates, the AND gates, the OR gates, all those are combination logic. We have then we have Mach 6 decoders, the ALU, which is part of the CPU, is also combination logic. You know this already. I took a lot of time and sweat to actually teach you that. Right? And then we have sequential logic where we talked about the latches and the what? Flip flops. Then we said that for the flip flop, we sample at the edge of the clock. Right? We know this already. And then we said that for the latches, we sample at the level. We know this already. So as I said, so for CPU design, we use both combinational logic and sequential logic to design our CPU. All the individual components there, all the individual components, the memory, all of them are what combination logic, right? We have some kind of control signal that we use FSM. We have to use an FSM to actually control it from one state to another. So from one state, read data from some memory. Then we go to another state, maybe perform some operation. Then we go to another state. So that's how the control works. And then the control unit uses the sequential logic, the flip flop, the latches to store some kind of information. Do you understand? Should I continue?
You said the individual components in the CPU use combinational
Yeah,
logic,
yeah,
but the control units use sequential.
yeah.
Now, the control units are part of the
Is the control unit not part of it? It's part of it. So
the only one that uses sequential.
yeah. Some of the things you guys ask for, it just dampens my spirit. Yeah, but that's fine. That's fine. Now, so we have always seen it. We said, or I might have said that the CPU, one of the CPU designs is a single cycle processor. You guys know what that means? A single cycle processor. I think I've been mentioning that for the past months or something like that. Anytime I said you're going to design a single cycle processor, that's what you're going to design. So, do anybody have any idea what a single cycle processor is, or a single cycle CPU? Anybody? Single cycle processor. Just even look at the just look at the name. What do we mean if we say a processor is single cycle? It does what in one direction. What do you mean by it works in one direction? A single cycle processor. We've been I think I don't know whether I've actually said anything about that. But what does it mean? If we say this processor is single cycle processor, nothing. Even I mean, just look at the naming itself. A single cycle processor. I think it should give you some idea about it.
It performs just one operation.
It performs.
Performs one operation.
That makes sense. Yeah,
Since I'm from one set of instructions at a time.
that also makes sense.
Performs a single instruction in a single cycle.
Yeah, that's it. they all make sense, right? Now, when we talked about when we looked at timing, we looked at we said the clock goes from 1 to 0, 1 to 0, 1 to 0. Right? This is how the clock looks like. We already know this. From this positive edge to this positive edge is this what one cycle. True of us. This is one cycle, right? So if we talk about a single cycle processor, and then we know what the processor does, it reads instruction, then it will fetch. It does a fetch instruction, right? It will decode that instruction. It will execute, right? And then it will write back to some kind of registers or something like that, right? It will write back. So all these processes are done within one cycle. The fetching, the decoding, executing, and writing back to registers or memory or whatever is done in just one cycle. Understood? That's what we mean by a single cycle processor, right? We can also have a multi-cycle processor. What do you think that one does?
That's multiple instruction, multiple cycles.
Multiple what?
Instruction. It does one instruction, multiple cycles.
Yeah. It does what?
One instruction, multiple cycles.
Not really an instruction in multiple cycles. So, as I said, this is the fetching, decoding, execute, right back. It's just one instruction, like add. Add, like, if we have something like add x1, x2, x3, right? Your CPU has to fetch this instruction. Your CPU has to decode this instruction. Your CPU has to execute this instruction. Your CPU has to write back to this register. So it means that there is just one instruction, and then it takes this number of steps in just one cycle. Understood? If you say multi-cycle CPU, a CPU is multi-cycle. What does it mean? Yeah,
Every step goes one cycle.
yeah. So the fetch will take one cycle. Fetch from memory, fetch instruction from memory. The code will take one cycle. The execute will take one cycle. So it means that it is multi-cycle. So probably this will be for fetch, right? From year to year it's for fetch. From year to year will be decode, execute, and then it goes on and on. So it has taken multiple cycles, right? So what do you think about it? Which one is better, single cycle or multi-cycle? Single cycle. Why? So
The more cycles, the less efficient. Time efficient.
yeah, I mean, common sense common sense will tell you that, but once you go, common sense will tell you that this is using only one cycle, right? So you might get the idea that it is faster. This is using multiple cycles, like 4 cycles. You might get the idea that this is slower, but it depends. What does it what does it depend on? We did you see that that's why we did the timing. We did something about timing, right? Now, if you pack instructions or if you pack operations into one to use only one cycle, your timing, your delay, your time has actually increased. The time to actually do all of this has actually increased, and then it means that your clock cycle has actually increased, right?
Will the cycle increase or the
The cycle, this, let's say your cycle was, let's say, let me just put it in there. Let's say your cycle use 1 second, right? Let's say normally your cycle uses 1 second, right? Now you're packing this operation, this into one cycle. So this one might look like, oh, it is fetching instruction. Then the next cycle is doing that. But because it's fetching just instruction, it's just reading one instruction. The logic within fetching instruction is so small that the cycle is too small, right? So it might use about, let's say use a 1 cycle, let's use a 1 second. You are doing fetching, decoding, execute, write back at the same time. Your cycle is not going to be just 1 second. It's going to increase your probably about 4 seconds or whatever. Did they get an Yeah.
So I thought the cycle was we declared the cycle ourselves. Like the last time we gave it 50 megahertz for the
Hmm.
cycle. So I don't
No,
know.
no. We said you saw that we said that the cycle, the clock cycle was should be greater than the what this TPD propagation delay of the combination logic plus the setup time and then plus what another one. It doesn't matter. All of this doesn't matter. All of these are set. The most important one is the TPD, the combination logic. How long it takes to execute the combination logic. So your TC depends on how long it takes your combination logic, right? Now, if you design your CPU to use only one cycle, it means that you are doing a lot in just one cycle, and then that will increase. So it means that this one will be increased. Now, if you are doing it at different clock cycles, it means that your fetch will have to take some cycles. Your fetch takes some time. Your decode, execute, all of them are done after fetch. Then you go and do this. After this, you go and do this. Those cycles times are shorter, shorter, shorter. So it will take the highest of these ones, the highest timing between the fetch, decode. That would be your TC, right? So that one, the TC might be smaller than when you're using a single cycle, right?
So you said,
Yeah.
so in essence, the multi-cycle processor is better than a single cycle.
That's why I said we are using once you are using single cycle, right? The main thing is you're going to use probably less number of gates, right? You're going to use less number of gates. And because you are going to control after fetching, you have to decode. You need to design a kind of control to say that, oh, it has finished fetching, now go to control, right? Or go to decode. We'll go to that. Now, in doing all of that, you're going to use more gates, right? So for motorcycle, you are using more hardware. For single cycle, you are using less hardware. But your timing, right? For motorcycle might be shorter. Your clock cycle actually, your clock cycle might be shorter than when you're using single cycle. Understood? Understood? Yeah, what? Huh? What is the need? Why? Oh no, what's that? All right. So yeah, don't dampen my spirit by just asking some question. That is yes. Ask.
Yeah, always in play and we go to
Yeah. Okay, continue.
I'm serious.
Okay, let's go on.
There all this multi other threads like that we have
That is in software.
multi
That is software.
that's software.
Yeah, this is hardware. We don't have that in
The
hardware.
hardware. So but in the code that they used to do, right?
Hmm?
The code.
Yeah, the software code. Yeah,
So in the code you can do multi-threading.
the software code. You mean the C or C plus plus or something like that? Yeah, I mean that one you are allowed to do multi-threading, but in hardware you don't do multi-threading. Hardware you are dealing with the gates actually. So how do you do
Let's say that
multi-threading?
when I'm going to buy a new laptop, they write thread
Yeah, they're talking about the software. The
about
software.
the specs.
Yeah,
They are
they're talking
talking
about the
about
software.
software.
Yeah,
I thought they are talking about the hardware. But they state it in their hardware,
yeah,
RTS 3060, and they write the threads. I thought it was hardware.
yeah. They're talking about the software that will run on the hardware. So, any other question? What's that? Any other question before I continue? Any other question? All right. So the single cycle is made up of what? We have ALU mainly with two inputs. Where does the input of the ALU come from?
That from the register.
Register file, right? So the register file is directly connected to the what? ALU. We know this already, right? Then we have memory. Two types of memory. We have the instruction memory, data memory. Now, why do we have two here? Yeah.
But this is a different architecture. This is at this Java.
Uh,
Where
eh, eh,
the data
eh,
memory and then the instruction memory are
yeah,
related.
of course. But another reason why we have the two here. What are we designing? We are designing a what?
A single
A single cycle processor, right? So why do we need two memories for a single cycle processor?
So I was fast slide.
No, 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 masa.
I mean like fast fetch. Because if I'm around here, I'll
search.
fetch immediately. If I'm around here, I'll search
Search.
immediately.
You fetch what?
Data.
For the two memories, right? One is for only instruction, so that's where you fetch your instruction from. One is for data. It means that you can store data there or you can retrieve data there and give those data to the register file. Those data don't go back to the other memory. Yeah. Master, you were. Yeah.
I think the reason why we are using two memories is because so that we can call, we can fetch and then store at the same time. Because we are doing everything at one time. So if you fetch the instruction, you have to be able to store it and then
Yeah.
store it at the same
Makes
time.
sense.
To reduce time because you have to fetch from here and then fetch the instruction process from data from the instruction from the so it reduces time for you to go and come
Mm,
back.
okay. That also that makes sense. But overall, right, we talked about single cycle where we are doing everything in just one cycle, right? So once we take once we take something like let's say store work, right? Once we are storing work, what do we need? Now we need the register where some data is, and then we have to retrieve that data from the register file, right? Register file, and then we have to go and store that data in some memory location, right? Right. So we need that, and then we need some what is called the offset, and then we need the memory location, the offset, and then
The
the
base,
base
base location.
the base location, right? That's what we so we take the base location plus the offset. That will give us the memory location, right? So now if we have only one memory, right? That part of it is storing instruction and part of it is storing data. How do we achieve this with single cycle? Now the single cycle means that we have to fetch instructions first, right? So once you are fetching instruction first, the next is how do you come and write back that data because you have only one port, only one address for fetching instruction and then also fetching data. So you can only fetch instruction at one time and data at another time or store data at another time, right? So you cannot achieve a single cycle kind of CPU with just one memory. It will take multiple cycles for you to be able to do that, right? So you need two memories, right? One for storing instruction that you retrieve, and then one for storing data, so that you can actually read instruction and retrieve data at the same time. Understood? Does it make sense? Right. Now, another very important component of the CPU is the PC. We talked about it, right? The PC is also a register, like the register file. But for the register file, there are several registers within that file. The CPU is just one register, probably 32 bit, right? The PC is just 32 bits, and then we get the function of the PC. We said, what does it do?
Points to the
It
next
points to
location
the
where it
next
needs to be read.
What?
it points to the memory.
To the next memory location to be read.
Yeah, that's what it does, right? Points to the next instruction in memory that should be executed, right? whatever. Understood? That's the function of the PC, which is also a register. Now, you should know that once the PC points to that instruction, the next one, the PC will increase to the next instruction, right?
Yes.
So now, if you combine everything with the control signals and everything, this is how your single cycle CPU, this is how your single cycle CPU should actually look like. And then we are going to see how the instruction flow through this architecture. Understood? Very, very easy, right? Once we break it down, right? All right. So now, uh, this is that we now have the technology to build our own CPU, and then that's what we are going to look at. Right. So first we look at the register file. I've already explained what a register file is, so we are going to go through really quickly. Right. What is it made up of? We say that this is how the architecture of the register file looks like. Right. We have already seen this before, but specifically for RISC 5, we say that how many registers do we have in the register file? How many? Huh? 33. How many registers do we have within a register file? Huh? Somebody said three. Registers do we have in the register file? We have our register file. We have a number of registers inside there. Number of registers. Aside from X0 to what? X31. Yeah, so we have 32 registers within the register. But we have 32 registers within the register file, right?
There was misfighted. Misfighted.
So
There was.
there are different versions, and I explained that for the different versions, this 64, 128, 32 means what?
The number, the width,
Data width
the data width.
from here to here is the 32, 64, 128. But for base 5, we have a fixed number of registers, 32. Right? So you can have RB 64, we'll still use 32 registers, but the width of each register will be 64. Understood? You can have RB 128 version of the RISC 5. It will still use 32 of them, but the width will be 128. Understood? So now for this register file, what is the data width? 54.
So what's the question? What's the question?
And I'm coming, come. You have just nowhere. You have just. Now wait. Let me get the thinking of. So why is it 64? Uh-huh. Where is the 32 by 32? Hey, that means that you have failed question 2 of the exam. Or some, because all I give you is you have a 32 by 32 register file. What is the data weight? Then you said 64. You have gone. Nah. So if you have 32 by 32, what does this mean? Understood? Alright, so this is the register file, 32 by 32. So it means that our data width is 30. What? So it means that our data width is what? 32 bits. Right? This register file has 2 read ports. As you can see on the board, just look on the on the board here. This register file has two read port, right? QA and QB. So it means that we can read from two registers at the exact same time, but it has only one write port. Page 32. It means that we can write only to one register at a time, right? And then we can only write this one. This register file has a write enable WE. Have you seen it? Write enable WE. So it means that before we can write, we have to enable it. You have to make write enable logic 1 before you can write. If the write enable is logic 0, we cannot write to it, right? Then we also have the RWRA RB. What is RWRA and RB? What what is a RW? Huh? Read word. Hi, but we have done this like some weeks ago. RW. What does it mean? Read right. R then your case what W. Huh? Yeah.
The register right now.
Register what? So how does it do? What does it do? The RW. Now look. Even if you know, even if you don't know what it means, right? The word, but look at what it does. Look at RW, RB. How many bits is it? How many bits? So what does it mean? Hmm? Yeah, I'm coming. That's right. That's right.
It's the very location for the very location.
You are almost there.
There is no memory location. Out of the selector that allows us to write. It's that as a selector. It said
Now, as they check the number of bits,
it's like this can accept up to 32.
and so he was on the right path.
He said memory location.
So just look at it. RW, RA, and then RB, right? We have 32 bits, one write port, right? One write port, right? We have how many registers within the register file? So it means that how do we write to the register file? How do we do it? What do we need to write to the register file? What do we need? The write enable, huh?
The register, right?
And then the algorithm.
We need why do we need the RW? Ah, you guys were
To point to the location.
yeah, that's what you're saying. Yeah. So we have 5 bit because we have 32 locations, right? So how do we write to the register? We need the data itself through the write port. We need the write enable, and then we need some address. Where are we going to write to? Right? So the RW is the write address. This thing I've already said it already. And then we have RA and RB. Why do we have RA and RB? Anybody? Yeah.
To enable which outputs.
Not enable. Anybody? We have already. So how do you read from this file? How do you read from it? What do we need to read from the register file? Hmm? You need write enable again. Have you seen any have you seen any read enable here? So this register file has no read enable. To read, we just need to give it a what? An address of where we are reading from. But we have 2 ports, so we can read from 2 registers at the exact same time. Have you seen it? So it means that we need RA for QA ports. So once we give address RA, where is also 5 bits, so it means that we have 32 locations. It can read from one of the locations. It will give that data on that register to QA, and then we also give it RB, which will give the data, the 5 bit data. It will go and read from the register file and give it to QB. Simple as that.
Sir, so there are also there are 4 bits.
What? Pointers.
Yeah.
Maybe
You said there are two registers.
in C code, yeah, you say they are pointers.
Yes, yeah.
But in hardware, you say their address. So RA is read address A, RB is read address B. The read address just means that we have given it, we have five, we have 5 bits. We can address 0 to 32 or 0 to 31 registers. If I give RA address probably 5, it will go to the register file and read from the location 5 and give it to QA. QA is the output port. You give to QA. Then you give, if you give RB register, let's say value 31, it will go and read from the last register file and give it to QB. That's how. So they are addresses to read from the registers. You give it an address and then it will read for you. Yeah,
There are two addresses, RA and RB.
yeah.
So when you want to write,
When you want to write,
yeah, when you want to write,
I've already explained how to write.
yes, I'm saying something. It means that you can only write one at a time because we have one
Yeah, yeah,
point.
yeah. No pointer address.
See the read address that will point to which address you should take.
Uh, how, however you understand it. Yeah. Hey, my my energy level is always like this. It starts like this. Then once you ask the question, it goes. So now I am around here. It's going down. I explained that. I explained first that to write, right? To write to this register file, what do I need? I need an address where I'm writing to. That is the RW. Right address. Even though it is RW, it just means right address. And the RA is read address A. RB is read address B.
The result is
Given
whatever
to
QA
yeah, yeah.
and QB respect.
Yeah.
Is there a way that we can have R, just one R for both of them, but maybe instead of giving it five bits, we're giving it 10.
And then what will you do? So now wait. Keep quiet. What is that? So do you want to design your racer file to have only one output? Okay. Your racer file has QA and QB, but you want that your you want to use only one, as you said, pointer, right? One address location, right? So now, what will be the number of bits?
Maybe instead of making it five,
So you make it. This is 10, right? Right. So now understand this. This array it's just like okay, it's just like a number. It's just a number you are choosing from probably. So if you do it 0 to this, so and then it takes that number and goes to search within the registers which number does it correspond to. So now if you make it RA to be 10, right? So now it means that the possible thing you are doing is that once you need another logic, right, within it. Even though you have made this 10, right, it needs to take part of it to give to QA and take part of it for QB. So essentially, what you have done is that you have done almost the same thing, but now you have shifted it into it itself, right? So maybe from 9 to probably what 5 is meant for QA. So it looks through that memory or it looks through that data. It's a data 4, 5, 6, 7 or something. Then it does that, and then from 4 to 0, it also picks from there and then reads from another and gives it, right?
so it's possible.
Yeah, of course, it depends on you, but there's an
But if you give it 10 days, that's like 1024. Like in the background, that means you have 1024 registers. If you give like I will give 10 days.
so that was where I was trying to get to. So, but the point is that you need to be careful the number you give it. So it means that you must be well aware that this can only go from what 0 to 31, and then you must be aware that this can also go from 0 to 31. That one you must be aware. Once you give it any number at all, it means that it will go and it will mess everything up. Understood? So I continue. This is just the register final, and then I thought I would have even gone faster because I already explained this one already. Right, so we have 32 registers within the register file. A very important one is that I said something about about register X0. What did I say about it?
Hey, it's always zero, like zero.
All right, yeah, that's correct. The register R0 is always hardwired to 0. Now, this is just an objective question for you to answer. So, can anybody answer it? I've already explained this already. Very, very easy, very simple. Can anybody answer that? Master. If you have the slides already, Master. So, what's the answer? I have RV 64, right? What will I change? The register file we already looked at. This one. This one is what? RV what? 32. So what will I change to make it RV 64? Yes.
We change the view, RD,
So
and then
what is the answer? A, B, C, or D?
I will change all
Just look at it. What will I change? Eh? Okay, now let's go. B. C. So we have A, B, C. No, wait. C. Please keep quiet. How many people say A? Wait. How many people say A? One, two. How many people say A? A. Guess your hand. Please, how many people are saying A?
7, 8.
Okay, A. 2, 3, 4. Then A. So about 4 people are saying A. B.
So hold on.
No, you yes. B. 1, 2, 3. B. So C. I B. About 4 people are saying C. Correct. So and D. And then I don't know. Okay.
None of the above.
You the none about you. So means that you have changed your answer from A. Yeah. Okay. So all of you should choose your captain. So who said B? Okay, your captain. Explain why B. Okay, speak. Keep quiet. B. So B is RW, RA, RB. We changed from 5 to 6. Why? Hey! Upon explaining
Say if I do that, if I choose what I'm choosing, it means I'm saying that
you have increased the number of registers, so now you have understood. Right, okay, so now B is wrong. C. Who says C? Yeah, I saw you. So explain. C is what? C means that the right is 32 from 32 to 64, right? Then we change RW from 5 to 6. Now we have already explained that RW. Want to change RW to from 5 to 6? You have changed from 32 registers to what? To 64 registers. They're not registers. But we are talking about only the wave. So C is what? From A.
So we are only changing
Please, please keep quiet.
the weight of the registers.
Yeah.
So we have to change A, W, A, and B. If we change R, W, R, A, and R, D, it means you are changing the number of registers.
Yeah, that's it, right? So as I said, and I already explained that we have RV 32, RV 64, RV 128, and I said this has to do with the wave. None of the above.
And the reason why the reason why I still know about that, I just explained
Right, that's the answer. So it's A. Only the wave. So now for the single, so we are going to now talk about how the single cycle processor actually looks like. Oh, nah. We talked about register file. Then we are going to talk about memory, and then we have two of them, right? The instruction memory. You are now about to look through your book. Then now. So this is a 32-bit address. So another question. I think question 3 also. So I gave you register file, right? 32 by 32, and I said label the pass or whatever. No, not the pass, but give me the data wave for or the number of bits for each of them. So for the data for the memory to, I would say this is what the 32-bit address, right? This memory is 32-bit address memory. What does that mean? Understand. Please always take time to understand the question, and then understand the words used in the question, right? Always think carefully. Just always take your time, right? Take your time. Now, 32-bit address. If I say a memory is 32-bit address, understand what does that mean?
it means that the memory has 32 address. It has 031.
It means that yes, of course, the address group is 32 from 0 to 32. 31. That is the address script. That just common sense, so it doesn't matter. But what does it mean? If I say a memory has 32-bit address, how many locations are within the memory? Ha! Let me write that. Now, I did here. Now I'm here. Ha! 32-bit address. Anybody else? 32-bit address. Yeah. Pardon? It can go. Nah.
So the question is how many? The question is
A memory has 32-bit address. Right? How many locations are within the memory? 32. So, what does RA mean?
read address.
Why is read address 5?
Because it's 32.
So it means that the number of locations within the register file is what?
32.
There are 32 there are a number of them, 32. So the read address is what? 5 bit. It's 5 because you take 2 to the power 5 locations within, or 2 to the power 5 to select from. So if I say an address, this memory has 32-bit address. What do I mean? How many locations are within this memory?
It's more than that. It's five.
Yeah, so it means that you guys feel this question, the other one too. So you understand that you are going to get around.
We have to understand the equation.
That's why I always take my time and draw the memory. It means anytime I do anything, I always draw the memory. Oh, this is memory, and I always do something like this. That means the locations, right?
As we said, we have five.
Within the what? 32-bit address. I've gone back. See, I've gone back to explain how we got the R5, the RA. We said RA is read address, and then we said the RA is equal to 5 because we have 32 locations to the power 5. The RA is read address. This, I have a memory that has 32-bit address. How many locations are within that memory? I have this memory, right? The memory has 2 to the power 32 addresses. 2 to the power 32 locations. Yeah?
I said, no.
Okay, you wait. I said that when you take memory, or when you take the memory, the register file is just the same as memory, right? Because you are addressing some locations within a register file, right? So now, if I have a register file and I say that the read address or the write address is 5 bits, right? That means that I take the register file. Inside the register file, the number of registers within it is 0 to 31. Right? For let's say RA or RW is equal to 5. It means that I have 2 to the power 5 locations within the register file. And 2 to the power 5 is equal to what? 32. The same with memory. If I say this memory has 32-bit address location or 32-bit address, it means that I have memory here. I have a number of locations, right? How many locations will I have if I say 32-bit address? Now, 32-bit address means that the width of the address is 32. 0 to what? 31. The width of the address. And then how many locations can I address with a 32-bit address? 2 to the power 32. So I have 2 to the power 32 locations within my memory. I'm on life support too. Hi, life support, right?
Wow.
I have to go over again. For which one? Register file, but you understand the register file. Okay, right. This is my memory, right? You see that it's the same as. So you always be giving. This is memory, right? You are giving the address with. You are giving the address width of your memory, just like you are giving the read address or the write address of write address or read address width of your register file. You always be giving the address width of your memory, and then you are saying that the address width of this memory is 32, right? So when I'm just saying how many locations can there be with a memory with an address width of 32 bits, right? And then we said that it's just as simple as 2 to the power 32 locations within the memory, right? Because we have we have the memory here. We have a number of locations from 0 to a number, and then that number will be 0 to 2 to the power 32 minus 1. Understood? Shall I continue? Even this one, I shouldn't even go through distance. I thought I would have just even brushed through this one. So this is how the memory looks like, right? You have your data, you give your memory data, which is D in, right? 32-bit. What does that also mean?
This one.
The D in is 32, D out is 32. What does that mean? The wave is 32, right? I have a signal, a 2-bit signal, and then I have this 2-bit signal is very important because this memory is 32-bit. The wave of the memory, right? We have a number of locations. Our wave is what? 32-bit. Right now, within your CPU, you can actually read from either the whole location, right? Which is what? 32-bit. Or, and then that one, you can use an instruction called what? The store word or the load word to read or write to these locations. So once I use LW, store word, LW, load word, it means that, and then I said a word is what? How many bits? Half word is what? A byte is what? A nibble is what? Okay, right? So I can use store word and then load word to load the entire, to load or store the entire 32 bits, right? But we also have some instructions which are SB, right? And then we have what? I think S what? H or something like that. And stuff like that. Right? So we need a way of telling, or we need a way of reading just 8 bits out of the 32, or reading 16 bits out of the 32, or reading everything. Right? So that is what the 2-bit there is for. So if the 2-bit is 00, if the 2-bit is 00, it means that we are reading the word, we are reading the entire thing, right? If it's 01, we are reading a byte, we are reading only 8 bits, right? It's on the board. So if it's 10, we are reading half word, 16 bits, you're reading 16 bits from this location, from one of the locations, right? And then we have 11 to the right way. Understood? So now, so we said we have two type of memory, right? The instruction memory and then the data. What do you think the difference are? In the architecture, what is the difference between the instruction memory and then the data memory? In the architecture itself, just look at it. We are looking at the architecture. Yeah, 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 yeah. Pardon? For the data. Yeah, I mean, that makes sense, but that's not entirely what I'm looking for.
You are asking about the temporal differences, right?
Yeah, yeah.
To me, I don't see any
And
difference.
so say you don't see any difference.
I don't see any difference.
Okay, we don't see any difference. Okay. Anybody else? Please keep quiet. I want the difference between the instruction memory and then the data memory. Now, huh? Oh, no. Yeah, okay, yeah, probably. So what does the input that? No, master. So now think. Once, once, once we talk about this memory, right? Think about your actual PC. think about ROM. Think about RAM. What does your ROM do?
Stores data permanently.
What does these two do in your actual
One is volatile.
one is
One
what?
volatile.
Volatile.
One is one volatile.
Then what?
Store the data memory.
One only
One,
has
one,
reading, one has write.
one keeps the.
Oh wait. Yeah, that's a very important point. So
One reads, one writes.
an important point.
The rum
It's
does
okay.
read,
It's okay. Yeah.
and the rum does read. I'm just telling
Yeah.
you.
So now, once we talk about instruction memory, right? We are talking about something like ROM. Now, for ROM, you store your program in the ROM. The ROM does not change. Continue.
Because
But
they say,
When do you have starting date?
you were saying something. I know. Continue. I said the ROM. You store your programs within the ROM, right? The RAM is for like storing data, your intermediate data. Let's say your ROM says do this, and then that kind of data will be fetched from the RAM. So the RAM will be for your data here, and then your ROM will be for the instruction memory. Now the clear difference is that, right, within you have your instruction memory, you have your data memory. Now your your ROM must not give you a capability to write to it. Once you have a program stored on it or some instructions stored on it, you don't really have the opportunity or the ability to write to it. So what it does is that the ROM only has, or for this one, for this instruction memory, we have only address. You give it only an address, right? You give it only an address, and then it has only another port, which is what data. So one port, give it an address, and then it will go into that location, fetch, and then give it to that data, and then give it to this port, data port, right? So for here, you have designed a ROM. If you do something like this, because can you write to this one? There's no write port. Only give it address, it gives you data, right?
And then the wrong.
Hi. Funny. Master, but you, like you are just actually killing me, pal. How this guy answers? Listen carefully. Always listen carefully, right? Please keep quiet. Always listen carefully, and always listen. Listen. Just like what your what your CPU does is that it will listen. Let's say it will fetch instruction, and then it will decode that instruction, right? It doesn't jump from just fetching the instruction to execute. So it will the decoding means what? It's understanding the instruction, right?
Yes.
But you always jump the decoding side and just go to oh, it's true. So I said, as I said, for the instruction memory, you only have an address, and then you have your output. Your address is the input to the memory. There's no there's no way to write your data. There's no way to even write your data to only address. Give it an address, then it gives data to the output port, right? For your RAM, I'm not saying, I mean, for what we are doing, for the RAM or for the data memory, you have to have the ability to write to the data memory. So you have your data here, right? The data in, this is the data in, this is the data out. Data in to write to, you must give it a what? An address also, right? Remember, give it right enable, whatever. And then once you do this, an address plus data in, and then you have your data out, right? Depending on the type of instruction memory, you can have separate addresses for writing and then for reading. It depends on you. That one entirely depends on you. But the main point is that for the instruction memory, you cannot write to it because there's no port for data in. But for the data memory, there's a data in port where you have the ability to write to it. Simple, right? Understood? Understood? All right, all right, all right. So now this is how, in actual fact, memory is memory is arranged in your CPU, right? Have you seen how it's arranged? Now here, once we arrange memory like this, it means that how, how much data can each location take? So anytime you see memory and then the the addressing of the memory is very important. You have to look at the address. Look at your far right, right? That's the memory addresses. You see from 0, 1, 2, 3, 4, 5, 6, 7 upward, right? Once you see, once you are giving memory, you have to first of all look at the addressing. How is the memory addressed? And then that will tell you the data wave of the memory, right? Now, once we have a memory that starts to label each location as 0, 1, 2, 3, 4, right? It means that it can only take 8 bits. It's 8 bits per location, right? Once you see a memory, then you just look at the address, you just look at the right, and it's 0, 1, 2, 3. It means that that memory just can take only 8 bits. Now, once we see a memory that with a data wave of 32, right? I think I said this the last time. Our addressing of the memory changes. I said in memory we do byte addressing. Byte addressing. We are addressing each byte. So if the memory is 8 bits, we address it with 0, 1, 2. Then it will be able to write or read from each byte. Each byte, 8 bits, 8 bits, 8 bits, 8 bits. Right? Once we have a 32-bit memory of data waves, right? Our addressing will change. Because we are addressing each byte, you have to start from 0 to 4, 8 upwards, right? So it means that each of these locations is 32. And then once we give it a 0, it means that we are reading here, here, and here. 0, 1, 2, 3. Then our next is 4, 5, 6, 7, then 8, 9, going, right? So once you are giving memory, you have to look at your left hand side, the addresses of the memory, and then you can determine the data wave. Understood?
So with the 32,
Yeah.
now you'll be rating 1, 2, 3. Each of them is equal to 8 bits.
Yeah. Yeah, of course, yes.
One,
It's 8 bit, yes. Understood? Shall I continue?
Another is 1, 2. So this one is
So what do you guess this one is? How much data can each location take? Which is 1 byte. So that's why we have, you see, 0x. This is what? How many bits? Yeah, this one, I'm dead. Ha! And this one, I'm dead. So if I have something like 0x, 0.5, this 0x just means that these numbers are hexadecimal. Hexadecimal means each number is 4 bits. 4 bits. So you add a 4 bits plus 4 bits. Yes, 8 bits. So where does your 32 come from? That's why I said you take the instruction, you decode first before you answer. Always 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 think. Once you're giving the question, always think. Then you understood. Shall I continue? Huh? No, it's fine, it's fine. I mean, so now we have looked at all of this, right? We have looked at all of this. The memory, register file, all of that. We have looked at the PC also. I think you guys know what the PC is. Right? So now, so to make a to make a computer, we need to store, or we need a program. Quick. Do you guys know the history of computers? At least you guys are doing what? Computer engineering, right? At least you must know something small about computers. Yes, increase the speed. Please, the history of computers. Does anybody know? Master, you don't know. Yeah, yeah. Let's go. It started with what? Abatos. Abatos, yeah. Yeah, yeah. Please keep quiet. Yeah, yeah. Yeah. That makes sense. So now, anybody else?
I said like your computation started when there was a war between
Now,
I think Germany and
the rest of the world.
yeah,
The Germans.
and they wanted to
The
they wanted to
Second
bring
World War.
the German the encryption code. So one man wrote a code that
Yeah. Have you have you watched the imitation game? What is the title of the movie? Imitation game. Imitation game. So at least, in case you come to class and you don't pay attention, at least pay attention to your movies. The history of computer can be linked to that movie he is actually talking about. Directly linked to it. The stored program concept started from that movie he's talking about. So at least if you don't pay attention in class, movies too. Over. Right? So he's talking about the imitation game. That's that is a movie. You see, at that time, right, they were using the tubes we were talking about, the vacuum tubes, right? And then they had a computer at that time called what, ENIAC. Yeah, you guys already know that. But they had a computer called ENIAC. Is it IC or something, or IAC? What? Electronically numerical integrator and computer, right? That's where the tube started from, right? So what this could do is that this could not store any program, right? What it does is that there's an interface like this, right? Divided into 4 panels, right? You have some slots here, and then you have some slots here, and then some slots here, and then you have some LEDs, some light bulbs here that will display your results, right? So to do any calculation, it could do addition, multiplication, subtraction, or something like that. So to do any calculation, they are built the tubes behind this one. So you put the slot. Let's say this is for R, right? You put some pin within the slot, right? And then you give it the number you want is here. Let's say it's A, B, right? You now give it a slot. You now give it a slot to indicate the number 0, 1, 2, 3, whatever. And then you give it another. You put some pins within this slot here to give it the another number, and then it will give you the results here, right? So this was not, it means that the program was not stored. It was programmed by some people, right? You program it manually. And then those kind of programs were actually done by only women. So at that time, once you refer to as once you mention a computer, you are referring to a woman because she's the one who does the programming. Pick the slots and then put the pins inside and do the calculations. Right?
like human being woman.
Yeah. So the first programmers were women. They were doing the slotting, right? Understood? But you see that this one has not stored any program. You have to do it manually. So so probably du- during the war, right? The Second World War, the first one of them. They had the the other party. The Germans had a machine called Enigma. So they will actually encrypt data or encrypt a message using that machine, and then they send that encrypted message to their soldiers on the field that go and bomb here, go and bomb here, go and bomb here. So the English had that machine, but it's very important in terms of encryption, right? What do you need to encrypt? You need a key. Once you have the device, you don't have the key, it's a waste of your time, right? Have you guys done encryption before? So you know how it works. So you take the message, you have a key, you have a key, and then you get your what? Ciphertext, right? What is the basic? What gate can you use to do encryption? You guys have already done encryption, so okay. I am a hardware engineer, right? So anything relates to gates. So now listen. You have look at all the gates, AND gate, OR gate, XOR gate, all of them, right? You see that. Let's take a. I have a number one. This is my what do you call it? Plain text, right, or something like that. I have another number one, right? This what my what key, right? This one side, right? This is the sender. This is the receiver, right? The receiver has access to what? Ciphertext, right? The receiver also has the same key, this same key. There's somebody in the middle. That person is looking for the key, but that person does not have it. Right? So which gate can I use to do this? And then use the same key to be able to get the value. Yeah. Eh? The NOT gate has only one input. The NOT gate has only one input, but I have two inputs. The plain text, the key. The XOR gate. See, now just look at it. Just look at it, right? This is my XOR gate. I have two inputs. I have one output. This is this is the basics of encryption, right? This one can be used to encrypt one bit of data perfectly. Nobody can break it unless the person has the key, right? Because okay, now here I have this. This is a what? XOR gate, right? I have my plain text is one here. My key is what? One here. What is the output? Right? I transfer this 0 to the person I'm trying to communicate with, right? I have a 0 here. I have my key. My key is 1. 0, 1, and XY is what? 1. So the person has been able to decrypt the plain text. The plain text was 1 here. The plain text is 1 here. So you see that the XOR gate is a perfect encryptor. Understood? So now, if somebody wants to break it, right? What will that person do? That person has access to the gate, because once you make up an algorithm, you do need to make it public. Once you design an algorithm which is used for encryption, you have to make it public. So the public has access to your gate. The public has access to another one, what does the public have access to? Yeah, the person has access to this one because you transmit the ciphertext. The person doesn't have what? The key. So the person can also take your. So that's where a hacker comes in, right? What the hacker does is that because the hacker knows the algorithm you're using, the hacker reverse engineers it, right? He takes the ciphertext right? The ciphertext is what 0 here. The person doesn't know the key. Let's say X. Then we are looking for an output here. So what does he do?
It tries about
Tries zero, one,
What does that mean? What is that term for? Brute forcing. So the person first of all tries 0 and then and looks at the output. Then the person tries 1. He looks at the output. But the important thing here is that
it doesn't
the
know.
person doesn't actually know. So once you try 0 and 1, the chance of you getting it right is 50%. And once you design an algorithm with 50% chance, it means that that's a perfect encryptor. Right? Understood?
Perfect encryptor.
Yeah. 50% chance of knowing whether. Understood?
Now, if it's perfect, the person can also find out. It's not perfect.
How will he find out? He doesn't,
Because
because
he
he will
also
keep
has
guessing.
50% chance of finding out.
And so it means that the chance is actually half. Like the chance of him finding out is like tossing a pen. Right? So now, from here, let's say the Enigma uses something like this. So what they had access to was the algorithm. So what the guy did was that he said, so what they were doing at first was that they were actually brute forcing. They were they were actually plugging numbers into that tube-like machine, plugging numbers, and then at times they get it right, but it takes a long time to get it right. So the guy said, okay, let me build a machine that uses a program that we can actually program all of this within that machine, right? And then it will be able to decrypt whatever we want for us. This one, it will take a very short time to decrypt. So he spent all his energy in building that machine. They became annoyed with himself because they were actually doing the tube. They wanted him to be doing the tube sound, but he said, nah. So he was building the machine actually. He used a long time to build the machine. They were annoyed with him for months. But later on, they saw that after the machine was built, he was able to design the machine, a stored program machine that was able to decrypt. And then from there, right, the war was actually shortened because of what he did. So some people attribute the stored program concept to him. What is his name? Anybody? Computer engineers, man. You don't know the father of your entire field. Alan. Alan Turing. Yeah. Okay. Yeah. Alan Turing. Okay, so that's where the stored program concept comes from, right? And then that's what we are using right now, right? And then also the stored program, some are attributing it to the Alan guy, some are saying it's von Neumann. He also wrote a paper after the war, right? After the war, he also wrote a paper about what a computer should look like. He said it should have a stored program, it should have input and output and stuff like that. But he didn't actually build anything. Concept, right? Okay, so now we have two architectures, the von Neumann and then what? Harvard. So so now let's go into details. How does the von Neumann architecture look like? Because you guys always mention the von Neumann Harvard. Yeah.
The human will have one memory part for data and instructions. That's the human.
Uh-huh.
He has one part for both instruction and data.
Path. What do you mean by the path?
This part.
One bus.
He has one.
Now you are studying. You have seen the architectures, the hardware architecture and stuff like that. So if you are talk like use the terms well. So the von Neumann architecture, what is it made up of? So you have your CPU. right? You have memory. You guys already know that there is a portion for storing code or instruction, and then there's a portion for storing data. The memory is divided into two. One portion for storing code or instruction, one portion for storing data. And then there's only one interconnection to it. So probably the address and then data. You give it address or you give it data or whatever. You give it an address and data or whatever. Right? Something like this. So you have this port that interconnects this. Now, so you can see that I have only one port for giving it an address, right? Only one port for address. So how does this, how do we know that it is instruction and how do we know that it is data? This address location is instruction and this address location is data. How do we know? Abi, you guys know, you guys always mention von Neumann. Yeah, Abi, is that easy? Von Neumann.
I say, how do you know the
Von Neumann stores both instruction and data in the same memory. How does it do it? So how, because we are giving it an address, and then once we give it an address, we read data, right? So how do we know that this address of giving it is instruction and this address is data? Yeah.
I think maybe the memory is very interesting, but maybe let's say after half, we give you that number for that address. After half, the number for
Yeah, so that concept, right? We call something that you have an address space. You have an address space, right? What we call the address space, right? So now, what you do is that you give it. This is a memory that's made up of locations, right? So this address space, let's say this is a 20 to the power 4 is what? 16, right? We have 16 locations, right? So we have from 0 to what? 15. Half of it is what? So, and then 8 to this, right? So what you do is that you have something called the address space. You say that this address space, 0 to 7, is an address space for data. And then 8 to 15 is an address space for code or whatever. It can be reversed. So once you give it any value or once you give an address from either 0 to 7, automatically it knows that it is reading from a data location or an instruction location. That's how the von Neumann works, right? Understood? So how does the Harvard also work? So for this von Neumann, you already know that you cannot read and write the data at the same time, right? So the von Neumann, the Harvard said that now let's have two of them. This is code or instruction, and then this is data, right? So we have separate address and data for this, and then we have separate address and data for this. So this has made it very simple. Your coding becomes very, very simple, right? Once you're not trying to once you don't give this one an address and data, it won't give you anything. Once you don't give this one an address and data, it won't give you anything, right? So it has become simple. Yeah.
That's this make the Harvard a single cycle.
The Harvard. Yeah, the Harvard can be single cycle, but the von Neumann can never be single cycle. Right? So now once you have this, but if you learn about memory, right, we have memory hierarchy. We have memory that resides within your CPU. That is the registers. Right? The registers reside within your CPU. That is, and then we have memory that is immediately outside your CPU for storing instructions and data. And then you have memory that lives completely outside the CPU. Now, trying to access them takes some time. Trying to access your registers takes a shorter time than trying to access the instructions or data memory, than trying to access memory from probably your disk drive or whatever. Right? So once you design an architecture like this, there's going to be a wastage. The memory here, you have memory here, separate memory here. So if this one takes a very small code and the one also takes small code, you have wasted a lot of memory, right? So what we now what they now do is that you have a modified kind of Harvard architecture that looks like Harvard, but it's not actually a Harvard architecture. So they call it the modified Harvard architecture, right? How does that look like? Do anybody know what that look like? So you take
two memories and then each of the memories have the instruction side and the data side.
yeah.
Most of the
So the modified Harvard architecture looks like this, right? You have your processor, right? This is your processor, right? And then you have your main memory, right? And then you have a memory that lives even outside the chip itself, right? Right? But the most so once you take your processor, you have the processor has a the control signals, right? The control signals, ALU, whatever, right? Now the first memory hierarchy is the register file. That is the first hierarchy in the memory, right? Now our next one is the instruction. What does this mean? Pardon? So we have instruction cache and then we have data cache, right? Understood? Now there is another one. Then we have the L2 cache. So now this instruction and then this data connects to this L2 cache, and then the L2 cache has a connection to your main memory, right? So this is how it looks like. So now think about it. So now here, once you have separate, you might think that you have separate instructions and data within the CPU. That, that is true because you have an instruction card, data card that has two separate ports, right? But once you come outside the CPU, you see that there's only one line here to your main memory. So you read your instructions or data to your L2 cache, right? And then your L2 cache now sends your instruction data to the instruction cache and then the data cache. Understood? Have you seen the hierarchy? And then from here comes your register file. Understood? So this one looks like Harvard architecture within the CPU, but once you look outside the CPU, it looks like von Neumann architecture.
So, but can you explain how you read and write at the same time? Using the main memory.
How you read and
How
write?
can you read and write at the same because
No. You are not reading and writing. This one has only one port.
So, but the Harvard was meant to be like.
So that's why I said look inside your CPU. Just forget about this. Look inside your CPU. You have two caches here. Instruction cache and data cache. So that's why they call it the modified Harvard architecture. So within your CPU, you can read and write to these two caches at the same time. Right? That is Harvard architecture. That's actually Harvard architecture. Come outside and then it's not actually Harvard. So this is what we call the modified Harvard architecture. Understood? Understood? Whatever. They call it the modified Harvard architecture. Shall I continue? So this is the Alan guy, then this whatever. So now should we take a break? What time are we supposed to close? Hey!
Let's move fast.
Okay, so now we have, so yes, how do we actually program and execute instructions on the RISC-V processor, right? Now we are going to see how the actual thing is done, the programming and then the execution of data or instruction on the RISC-V processor. As I said, I've already said that. I've already said that you fetch, you execute, you do what? You decode, you execute. But here, I think I've already said that you can only deal with one instruction at a time, right? You can only fetch, execute, whatever, everything in within one cycle, and then it's only one instruction at a time, right? So here, this we have the PC, right? The PC points to the memory location that has the next one, and then it will be read. That instruction will be read into the current instruction here. You decode it, you execute, and then you see that the PC has an adder. Why does the PC have an adder there? After the PC points, it will have to add PC plus one or plus four, depending on the memory arrangement, as I said, right? So our this is the basic one. The instructions is stored in memory. We have the register file, then we have the data memory, then we have some interconnections between them, right? So now this we yes already know. You program in your high level language, so it gets converted to your RISC-V instructions, right? Which is the assembly language, and then you can convert your RISC-V instructions to your machine code, right? And then that will be loaded within to your CPU. You have two classes of all of this. You already know. So now this is a very important question. Like, what does it mean for an architecture to be called load and store architecture? I explained this last week. Yeah, I think I explained this last week. Yeah, yeah. A B C O D. C. Data must first be loaded into a register before it can be operated on. Decoding. What does it mean an instruction is load and store?
Sir,
If the thing is in memory,
you should be able to load from memory to the register.
So in A, B, C, O, D.
The answer is data must first be loaded into the register before it comes. Yes,
A, B, C, O, D. Right, you see, right? Because the data must be loaded to register. For the load and store, as I said last week, it must be loaded into the registers before. Okay, so now this is your entire architecture, right? From the memory, instruction memory to your data memory. That's how it's arranged. And I said that within one cycle, you must fetch, decode, execute, access memory, and then you write back. Do all this within one cycle. That's what we are going to do, right? So we fetch instructions. So now the first step is what? We fetch instruction. Where are we fetching the instruction from? So have you seen that? The program memory is the same as the instruction memory, right? So you fetch the instruction from the instruction memory, and then you see that we have an architecture here. We have the PC, then we have an adder plus 4. You know why we have that? So it goes, the PC starts from 0, next is 4. So we have PC plus 4. So whatever. And then you must understand that we fetch 32 bits of instructions, and then we have seen how the instructions are encoded into 32 bits. We know that already. So we fetch our next is decode. What are we going to use to decode? We have a control unit, right? That will decode the various instructions for us. And then if you say decode, you know that, as I said, we have the instruction is 32. Then we have fields within the instructions. So the decoding just selects within the fields. We have the opcode, we have RS1, RS2, FANC7, FANC, whatever, whatever. So the decoding just selects within the 32 bits. It knows that this part is for this part of the opcode is for, let's say, addition or subtraction or whatever. So that's what the decoding does, right? It takes the instructions, and then the input to the control unit is the instruction itself, the 32-bit instruction, right?
So the
So this kind of question.
my question is, you see the width, the last part. There's that one thing that's still moving.
Yeah, yeah, yeah. Yeah.
So this is our instruction. So in the program memory, that's our instruction. So let's
Yeah.
say for example, the instruction is, let's say, an add instruction,
Yeah.
something like that. So the output is referencing the add, right? So why is that the control is connected like this? I don't get how the connection.
Which connection?
You see, the control is to determine. They are fetching, okay, add from the. I
You are
don't get
fetching
how
the entire 32-bit, right, to a control unit. So you have this. This is a control unit, and then the control unit will now separate those fields. We have the opcode, RS1, RS. So in case we are doing, let's say, add x1, x2, x3, right? The add will be here. So x1 will be here, x2, x3, and then some other functions. So what the control unit does is that it picks up this one, right, and then picks up the x1, and then the x2, and then the x3. Separates them into parts.
okay, so how do you put it in the program when you that we know that you have been an add instruction?
How do we input what?
So no, like I'm saying, like the address you have put in the program memory. Because the program memory accepts an address, it doesn't write, so it reads. So the address will select whether you're doing an add or something like that. Am I right?
Hmm.
So in
Yeah.
that case, like there's no write address. When we did the program memory, we had an address to locate which instruction you want to perform.
Yeah.
Right? So like I'm asking this diagram, how do we know how do we like the program memory just has an output and then the program contact.
That's why we started from the top here. We started from here. That's why we started from here. Here you write your high level language, whatever your C++. You convert that C++ to your RISC-V assembly language. That RISC-V assembly language get converted to your how do you call it, machine code, right? All of this is in software. That's not what we are dealing with right now. We are dealing with from the machine code. Once the machine code gets stored within your memory, how does it operate? That's where we are. So just assume that right now we have some instructions within that memory. Understood? Right? So from the decoding, as I said, the 32-bit instruction will get sent to the control unit, and then it will separate it into fields. That is the decoding, right? And then we execute. Depending on the instruction, you use the ALU or not, or whatever. It depends on the instruction. But that phase is what we call the execute. From the after decoding, you execute. Whether it's addition, subtraction, you're going to use the ALU. It depends, right? And then from there, we can actually also read data from the data memory or write data to the data memory based on the instruction again. It depends on the instruction, right? And then after all of that, we have to write back to the register file. It depends again on the instruction. It strictly depends, right? Okay, which of the statements is true? This is just the exam questions we are solving. Ah,
Says
there are objectives. The objective is plus one or minus one. If you get it wrong, then it's minus one. You don't guess electrical systems. Please hurry up. So where's the answer here? Why?
Yes, 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 yes. Because
C is what?
all instructions right to register.
It's A.
Say, but all instructions right
Not all
to
instructions right
register.
today. Register file.
So what instructions are
A lot of them.
so, but if you look at our
Only adding. We have the types of instructions, right? Yeah.
the right we are dealing with those that are on the board. And according to the board, all instructions are possibly registered.
The first one, A. All instructions require access to the program memory. That is correct.
Yes, but now it's
So all instructions write to the register file. No, not all instructions write. You say write to the register file, right?
so let's go back to the okay, no, not
I always say it depends on the instruction. Right now. Even let's say store where. Are you writing to the register file? You are storing something from the register file to memory. You are not writing back. You are not writing anything to the register file. So store where is an example that doesn't write to the register file. Understood? So where? Huh? Why? So I said you have store word and then we have load word, right? What does load word mean? Then what does store mean? Store word.
register to memory.
So so it means that last week there you went. Nice. Okay, as I said, we have so many types of the instructions. Right? We have arithmetic, we have memory access, then control flow. So let's see how the arithmetic or logical operations work. Right? We already looked at this one. So this is just a reminder. This is just a brief reminder of how the instructions are encoded. Right? We know that. We know that for the arithmetic and logic operations, we have the first 6 bits is what? The opcode. The next is what? The RD. What is RD?
Destination
Register. The next is func3, right? Well, our next is RS1. What is RS1? Source register 1. What is RS2? 2. Simple, right? So this is how the instructions are encoded. Then for the add and subtract, once we look at that sheet I gave you, or whatever, I don't know whether it's there or not. The add and subtract, they have the same func3. Right? Once we look at the add and subtract, they have the same func3, which is 0, 0, 0. Have you seen it? No, I don't think it's there. The numbers are not there. So just look on the board. You just look here. So the add and subtract have the same func3. So is it that they are 0, 0, 0, 0 and the 0, 0, 0? The same one. So it means that how do we identify whether it's add or subtract?
so based on the content.
So look, just look on the board. You see. Now the opcode 2 are the same.
All the outputs are the same, so you have to use the factor and second.
Yeah, and but the func7 is not actually here, so but you use that func7 to actually determine which one is this. No, so now here, if you look on top here, I have my machine code here. 110 whatever. Oh, I was pointing to this one. So this is a machine code, right? So can you figure out what the machine code is? What is it doing? So to figure this one out, very simply, we have to first look at
The up
the first 6 bits is zero what? Is 0110011. Oh, this is the
zero one one
opcode.
zero one one.
And then this opcode can be what? Add or subtract. Right? So we have to look at func 7 here to determine whether it is add or subtract, right? Right?
So what are you adding now?
So now because you don't know what func 7 is, you just let's say it's so we have func 3. So now here from the opcode we are doing what? Add or subtract. That we already know. Then our next one is what? RD1. What is RD1?
0010.
Sorry. So what is 0010?
That's
Now,
the
once you look at your add or subtract instruction, we know that it's either add or subtract, comma, add what,
RD destination register.
comma,
RS1 RS2.
comma, RS2. So here we know that we're doing add or subtract, comma. Then what is RD?
00100.
So what is that in decimal? In decimal, it's 4, right? 4 in decimal. So it means that our destination address is 4, comma. What is RS1?
RS1 is
Hey,
0100.
this is this. What is the RS? We have 01. What? Right? What is 2 to the power 3? 8. This is how you can get simple your decimal to whatever.
Thank you for that. Thank you very much. Thank you for the
This simple things for. So it means 8. What is our RS2?
RS2 8 plus 8 plus 1. That's what it is. I'm looking at it. That's what.
It's what? It's what? 0. What is it? 0 what?
1, that's 1, 2,
It's 4.
0 is 0. Where from the 011? So 0 what? 110.
So that's 6.
Very easy.
Is that 6?
You can see how easy that is. So you see that even though you look at this complex machine code, you might think it's complex, but once you break it down, you can see that this is doing add or subtract register. The destination register is 4, source register 1 is 8, and then this, right? That's all it's doing. Right? So this is actually an XOR. Understood? Because you weren't looking at the func 3. Look at the func 3. So once you look at func 3 100 with an opcode of this, you are doing an XOR. Understood? So here you are doing XOR. So you have seen how easy that is. You have actually decoded your machine code to your assembly language. Have you seen it? What? Maybe I don't remember.
No, he's asking a question from a point of view. He came with a
Ah,
question like this.
Again, the question again. Printed in black and white. How we determine the fact?
because you know the bits. You know that the opcode is 0 to 6. Bits 0 to 6. You know that my opcode is what? 0 to 6 bits.
Okay.
My next one is 7 to 11 bits. Next one is 12. So you have to, whatever.
So I just allowed this people.
Oh, now then it becomes very easy.
Oh, so you have to take one name.
At least choose something.
Oh, let's choose this one there.
Whatever. But this just means that this just means that you are doing X4, register X4 is equals to what? Register X8 plus register X6. Simple, right? And then it's just X or whatever. And as I get to. So how does it get executed using this? So you see that if I'm doing something like this, if I'm doing the XOR, X4, X6, X8 and X6, I don't need memory. Do I need data memory? Please keep quiet. I don't need data memory because I'm not reading anything from the data memory, right? So now here we assume that that machine code, right, is stored in the program memory, right? So how does it do it? So we will first of all have to fetch, right? So it will fetch this instruction. So you see that it has fetched the instruction, and then it will give that instruction to the control unit. So you see that the input to the control unit is the instructions, right? So the control unit will now divide those fields. So the next stage is decode. You see, it has decoded it, and then it has seen that, oh, we have 5 bits. We have we are reading from 2 register locations, right? X8 and then what? X6, right? And then our next stage is to execute, right? So it will execute is X8 plus X6, and then what does it do next? And then we saw that our next stage for that one was to go into memory, like some kind of memory. So here, because there's no memory, we have to skip it. We skip the memory because there's no memory. And then we have to write back. So we write the X6 plus X6 or this into the register file. And then the location was X4. So you have seen how it works visually. You see how easy that is. Do you understand? Should I continue? So this is how the instruction works for just XOR. Right? So we have
So that's if you don't have load and stuff, you get it in.
of course, what are you using the memory for? But it means that let's say you are building a CPU that only does register operations, right? So it means that if you add your memory to it, you have wasted a lot of. But if you are doing, if you in case you are building a CPU that does everything, it means that you must bring all the components inside there. The memory, register file, everything must be inclusive. If you are doing load, restore, add, subtract, multiply, divide, everything, right? You must bring all of them inside. So now our next is we have shift instructions, right? Right, and then again, uh, we have 3 shift instructions. We have SRL and SRA, and then the shift instruction just means that we have destination register. We have 2 source registers, right? So we take the destination register. Example, if you have something like this. Where is the mouse? If you have so we have destination register RS1, source register 1, and then source register 2. All we do is that we take source register 1, we shift it by the amount in the source register 2. So the source register 2 become the shift amount, right? How much am I shifting? Am I shifting to the left 4 times or 5 times? You know what shift does already. And then again we have SRL and SRA. You know what that means? We have 2 types of shifts. One is if it's steady Yeah, I think you guys studied numbers already. So we have S what? RL and SRE. What does it mean? They are all shifting what? They're all shifting right. So we are shifting to this point. We are shifting right. Right? So what does the LAA mean?
If you are opposite the sign, or
Shift right. Ah,
the
sorry.
sign.
So we are shifting here, right? What does what does a shift do? Now, if I have something like, if I have an 8-bit value like this, right? And I say shift right by 1, right? What do you think the value is? I have a value like this: 1 0 0 0 0 1 0 0. If I say shift right by 1, what becomes the value?
Zero
So
one
0 1
zero zero
0 0.
zero
Yeah,
zero one
I must have one person. Please, 0 one person should start.
This is zero,
zero
Go.
zero, one, zero, 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 one, zero.
Hey, I'm shifting right. Shift right.
By one.
Yeah, I'm shifting right by 1.
The machine value is one.
Oh, yeah, yeah, that's it.
Then why you not thinking
Yeah, what the difference? All right. So now, once I do something like this, once I do something like this, right? Once I do something like this, we have in numbers, right? We have what is called sign numbers, right? So now, and then the last bit indicates whether a number is negative or positive. So once I shift something like this, and then I put a 0 here, we are shifting right logical. We didn't care about the sign. So it means that if I'm looking at this value, and then if I'm looking at this value, I will say this in case I'm using sign numbers, this value is a negative number. But once I shift it, it becomes a positive number. So this is shift left logical. Now to shift right logical, we have to extend the sign. We have to keep the sign. The same procedure, we shift left. But the sign, this large base is a sign. That indicates whether the number is positive or negative. So once we shift it, we have to maintain the sign. Right? Arithmetic. Understood? Easy, right? Now again, again, another very important point. Let's say another very important thing about shifting. This is 0 0 here. So it will be 0 0, right? That we have shift left by 1. What do you notice once I shift left by 1?
right?
Right by 1. So this number was what? In decimal. No, what is it? In decimal 4. Once I shift left by just 1, it becomes 2. What have you actually done?
Change the number.
You have divided the number into 2. Understand? So in hardware, right, the multiplication and division is very expensive.
And also the change the number.
Multiplication and division in hardware is very, very expensive. It uses a lot of gates, right? So now what they do is that now if you have a number and then you are dividing a number or multiplying a number, that is to let's say you're multiplying, this is 4, right? And then let's say and I want to divide this one by 2, right? It's 2 to the power 1. So this one, what I've done is that I've divided it by 2 to the power 1. If I have anything that is divisible by 2 to the power some number, right? I don't have to do division. I have to just shift. So if I have, let's say, if I have 8 here, and then I say divide by 2 to the power 2. You know that 2 to the power 2 is what? 4. Right? So if I have 8 is what? 8 is, let's say, 0 0 0 1.
Zero zero zero.
8 is 1 0 0 0, right? And then we have 0 0 0 here. So in case I say divide 8 by 4, and then you know that 4 is 2 to the power 2. What you can do is that you can shift right by 2. Once I shift right by 2, I remove this one. It becomes 0 0. What is this? 2. So 8 divided by 4 is what? 2. Right? So once you're doing multiplication in hardware, and then the number is like 2 to the power 1, 2 to the power 2, 2 to the power 3, onwards, you have to just shift. Division or multiplication, it works. You have to just shift right or shift left. Once, so in case I'm shifting right, what I'm doing is that I'm dividing. If I'm shifting left, I'm multiplying. Understood? Easy, right? Understood? For the multiplication, let's say, for instance, I have 2. Let's say I have, let's see how it works. Let's say I have the number 4 here, right? The number 4, right? I want to do times probably 4. So 4 is 2 to the power 2, right? If I want to multiply 4 by 4, what I do is that I shift left by 2. So this 2 goes away, right? And then here becomes 0 0, right? So what is the number? 16, right? So 4 times 4 is what? 16. So I don't have to use the operator multiplication in the hardware. Understood? So once we are, so just take note of that. So let's do one last one in close. Just this one in close. So here, what do you think? What? So now let's look at this one carefully. Let's look at the machine code. What are we doing? Look at the machine code, right? The machine code is what? 001100. So it means that we are doing either shift left, shift right, or shift right arithmetic, right? So we need more information. What information can we use to get? So we have to look at function. Where function is 001. So here, what are we doing? We are doing SL. So we are doing SLL. We know that we need RD, RS1, RS2. So what is RD? RD is what? So 01. So, and then what? RS1.
RS1 is 001. That's for X4.
And then what is RS2? So X6. So I'm going with X6. So you see how easy that is, right? So this is just shift. So now when we come here, so it means that first we have to fetch again here. We don't need memory. We don't need memory for anything. So here we can do this. We can do this in 2 ways. Because we are not adding or subtracting. You know that once we are adding and subtracting, it is the direct values. We take A and B. We take A and B, right? But here we are shifting, right? So do we need the 2 values to enter into the register file? When we are adding, right, we need, let's say, the X5 or the X4, the 2 values within the add. We need them to feed directly into the register, into the ALU. The ALU, look on the board. The ALU has 2 inputs. The ALU has 2 inputs, right? One input and another input. Once we're adding or subtracting, something like that, we need those 2 inputs. But here we are shifting. And then the shifting just means that we take one register and then shift by the register, another register, and then we put it into this register. So we are not directly adding two numbers like that. So we need to read from, we can read from one register, and then we make sure that we give the control to the ALU another value, the shift value, and then it will just do the operation for us. This one here it depends directly on you. You can actually read both values from the two files, right? And do what you want to do anyway. Here it depends only on you. But some people always take that we read one from the register file and then we give the other value as a control to the ALU. Right? So this is how one of them works. So we need another signal to the control, to the ALU, right? From the program memory directly, right? Understood? So we fetch SAL X8, whatever. So we first of all fetch it. XAL X8, X4, X6 from the memory, and then we decode it. Have you seen how it works? So it means that we read one register file, but the other one is gotten directly from the instruction, right? And then we do the execution. We shift left by whatever that value, and then
How is supposed to be one by?
huh?
Since the area accepts it, if you give one by,
That's what I'm saying. It's your choice. However you want to do it is how you will do it.
but can we pass X0?
X0 to do what?
Since the all X0 are hard drives.
You can do it any way you want, as long as it works in just one cycle. That's your choice, right? So from here, then here again we escape the memory, right? And then we write back the value to the register X8, right? So that's how this one would. Let's close for today and continue another time. But okay, yeah. So we are done for the day. And I wanted to show you how to do the MESM, the